Welcome, conservation officers. Let's get right into this explainer detailing our national park's panda population projections. You know that if we're going to manage these habitats successfully, we really need hard data and reliable mathematical models to make those tough, informed decisions. So today, we're going to break down the exact numbers, the modeling process itself, and the specific timeline projections you'll need to do your jobs effectively out there in the field.
Okay, let's dive right into this situation report focusing on the specific growth patterns of our park's magnificent pandas. I mean, these incredible animals are absolutely the heart of our conservation efforts, right? But managing their population requires way more than just enthusiasm. It literally requires precise mathematical forecasting. We're looking at a very specific scenario today that essentially maps out the future of this entire habitat.
So, here's our game plan for today. We'll start with a quick habitat situation report, then define logistic growth. After that, we'll walk through the step-by-step model calculations, project the population timeline, and wrap it all up with some actionable habitat management insights. Let's get to it.
All right, Section 1, Habitat Situation Report, establishing the baseline. Let's look at the raw data we're currently dealing with on the ground.
This table brilliantly illustrates our starting parameters. Because, to project the future, we absolutely have to know exactly where we started and where we stand right now. So, a decade ago, at time 0, exactly 10 pandas were introduced to the national park. And over the past 10 years, we've seen some fantastic successful integration and breeding, which brings our population to 23 pandas at the present time. This gives us our two essential anchor points for any mathematical equation, our starting line and our current progress.
Now here's where things get really interesting. We're operating under an absolutely critical constraint. Sure, we have our current population of 23 pandas, but we can't just grow forever. Actually, our park has a hard, absolute limit of exactly 100 pandas. The bamboo supply, the territorial space, the available water sources, they all simply max out once we hit that 100 mark. And honestly, this upper carrying capacity is the single most important factor in how we model the future.
Moving on to Section 2, defining logistic growth, the S-curve. To figure out exactly when we're going to hit that maximum limit of 100 pandas, we need to apply some mathematical modeling to our data. So the crucial point here is really understanding the logistic growth model. Now, you might think a population just grows and grows at the exact same speed forever, right? But in nature, that simply isn't true. A logistic growth model is a mathematical construct where population growth starts off super fast, mostly because there's plenty of space, zero competition, and a ton of food. But then it inevitably slows down as those resources become scarce. When you map this whole thing out on a graph, it forms this distinct S-curve. It sweeps upward sharply at first, representing all that rapid early growth. But as the population approaches our maximum park capacity of 100 pandas, the line kind of flattens out horizontally, basically creating the top arch of an S.
Okay, Section 3. Step-by-step model calculations, finding the solutions. Next up, we're going to formally break down the exact mathematical process used to project our numbers, so you know exactly how these projections are actually generated.
As conservation officers on the front lines, you really need to know how we arrived at our timeline. First, we identify our known parameters, a population of 10 at time 0 and 23 at year 10. Second, we set our carrying capacity at a maximum of 100. Now, here's where the math actually works its magic. In a logistic model, the software basically takes the natural growth rate established in those first 10 years and then mathematically introduces the friction of our 100 panda limit. It calculates just how much that lack of space will continuously drag down the birth rate and survival rate over time. Step 3. We graph this resulting logistic equation in MS Excel so we can visually see that relationship. And finally, Step 4. By using the trace function within the software, we can literally travel along that generated S-curve graph point by point and pinpoint the exact years we're going to hit specific population targets.
Which brings us to Section 4, projecting the population timeline, critical milestones. Let's see how this all builds into our actual real-world projection timeline for the panda habitat. By tracing that S-curve in MS Excel, we reveal these absolutely critical operational milestones. Obviously, we know year 0 and year 10, but tracing further along that graph tells us exactly when the population is going to hit 50, 75, and ultimately 100 pandas. The model shows we hit 50 pandas at the 22-year mark. Then, we reach 75 pandas at the 33-year mark. And finally, we'll hit our absolute maximum capacity of 100 pandas at precisely 75 years from the initial introduction. Guys, these aren't just abstract mathematical numbers. These are the exact years your resource management strategies are going to be put to the ultimate test.
This data just brilliantly illustrates the slowing growth rate inherent in the logistic model. I really want you to pay attention to the intervals here because they are fascinating. Notice how it takes just 11 years to jump from a population of 50 in year 22 to a population of 75 in year 33. I mean, that is a rapid, explosive increase of 25 pandas in just over a single decade. But look at the next jump. To go from 75 pandas to our absolute maximum of 100 pandas takes a massive 42 years. Wow. That is the mathematical friction at work right there. That's literally the top of the S-curve flattening out in real time. As the park gets closer and closer to its absolute limit, space gets tight, food is contested, and growth just significantly decelerates.
And finally, Section 5, Habitat Management Insights, Actionable Takeaways. Now that we have our mathematical projections and we understand exactly how that curve behaves, how do we actually use this on the ground?
So let's translate this data into action. Conservationists must use these specific milestone findings to proactively manage park resources. First, you've got to rigorously track these milestone years. Year 22, year 33, and year 75 are your critical operational checkpoints. Second, prepare for that slowing growth rate. Definitely do not expect the rapid expansion of those early years to continue forever. Third, and honestly this is absolutely crucial, you must proactively manage space and resources as the population nears 100. Remember, you have a 42-year window between year 33 and year 75, where the population is squeezing into the final available percentage of the park's capacity. You really have to intervene before the habitat runs completely out of space, using these numbers as your ultimate guide.
All of this brings us to a vital, really provocative question for all of us park rangers and conservationists to consider. Look, we know the math. We know the logistics growth curve flattens out precisely at year 75. But once we hit that absolute mathematical limit of 100 pandas, what exactly happens to our habitat next? How on earth do we sustain an ecosystem that's operating at 100% capacity indefinitely? Well, that is the next great challenge for our team out in the field.